What's going on, everybody? You've had a chance to take a look at the central limit theorem, at least a very quick cursory introduction to it, most notably from a video that I showed you a couple of weeks ago in which a person was rolling some dice. And we noticed that the more dice that this person was rolling and adding up all the results for, the more normal in shape the distribution got over time. That's kind of a touch on what the central limit theorem is. But the reason why we have an entire chapter on the central limit theorem is that there's a lot more to discuss about it. You're going to learn the central role of the normal distribution plays in all of statistics. You're also going to see just how the parameters of that distribution change as we start to deal with sample means instead of individual samples. We'll also start to see just how those parameters change all the more as those sample means are of samples that are larger and larger sized. And that probably sounds like an awful lot of gobbledygook at this point, but you might have noticed that there was a place on your normal distribution sheet from Project 3 that looked like this. And in particular, I'm going to highlight this right here. There was this row in here that was called sample size, and I just told you to always just set that equal to 1, to not really deal with that. In this chapter, you're going to learn how to use that part of it. You're going to see what that's all about here. As it turns out, when we start to deal not with individual samples, but with groups of samples, we can actually change what the shape is, not really the shape, but the size of a distribution based upon looking at the dynamics of the sample, not just the dynamics of individual elements in the distribution. So let's take a look here at the central limit theorem and just how we're going to be working with this. We're going to be essentially talking about sample means instead of individual samples. That's the big jump that we're working with. If you recall, when we were working with the normal distribution before, we were always taking a look at individual data values. Individual data values here. Here we're going to jump from individual data values to samples, and it's going to give us a gateway into how to calculate things like confidence intervals and margins of error. So this is a pretty important chapter here, one that's going to be a gateway to so many other concepts for you. It's important that you pay attention for this. So we're going to be talking about how distributions of sample means change when sample sizes get larger and larger. Most notably, how do those standard errors change as sample sizes get larger? And I'm putting this out there knowing that you haven't yet been exposed to the term standard error. Essentially what it is it's the standard deviation of the results from a set of samples taken from a population, not just individuals from a population, but what are the results that we get when we take samples from a population? What are the statistics like for that? And as the statistics change, we have new ways of calculating z-values and probabilities from distributions from sample means. The formula is almost exactly the same, but it changes just ever so slightly. We'll also be making use of some finite population correction factors. We actually didn't realize this, but when we were calculating necessary sample sizes for Professor Howell's classroom, we were actually making use of finite population correction factors when we were making those calculations. Here we can start to talk about what those are. Okay, so let's take a look at a population here, a population of a very large number of people here. We can ask ourselves, what's the average resting heart rate of this population? And since we're dealing with a population, we use our legendary Greek values to describe what's going on here, Greek letters rather. And it's the Greek letter mu for this. That's our variable to describe the population mean here. But we can also ask, what are the statistics going to be when we take a sample from this population here? First of all, what's the mean resting heart rate of this sample? Well, let's say that we do take a sample of this and we get a sample of 74. Well, now the best indication that we've got of what the population mean is a resting heart rate of 74. But just how accurate is that? And how much more accurate could that be if the sample size got larger and larger and larger? This is the kind of stuff that the central limit theorem can tell us about. So the difference between the sample mean and the population mean is the sampling error. Yes, we've got a value from the sample here of being of 74, but we'd be kind of foolish to say, well, that's what the population must be. That must be an exact replica of exactly what the population mean is going to be. We would anticipate that there's a little bit of error between those two things. And that error is going to be inevitable because of the fact we're not looking at the entire population. As long as you're looking at a sample, you're always going to have sampling error. So sampling error is something that's inevitable, and we can actually quantify it. What's not so inevitable is what we call non-sampling error, which deals with erroneous sampling here. We'll talk about that in just a moment. So let's actually see about if we can describe what's going to happen if we take multiple samples of the same size from this same population here. Let's assume that there's a normal distribution that describes the resting heart rates in this entire population here. But we're going to take not just one sample of, say, 100 people, but we're going to take multiple samples of 100 people from this population. And we're going to get values of the average resting heart rate for all of these 100 people. Okay, so what do we expect the distribution be of the averages of this population here? So let's talk about this. Well, I'm going to actually show you. I actually did a simulation here where we have 10,000 samples here, and we've got some raw data. And I'm showing you here what the original data looks like, just up above here. It's a distribution between 0 and 100. And as you can see, each number in the distribution occurs at about the same number of times, as you can see here. So we've got quite a few data values here. There's a little bit of variation, but it's pretty flat as far as the distribution. So this is pretty close to a uniform distribution here. So my first question to you is, what would it be when we start to take a sample of 2, a sample of 5, a sample of 10 of these samples? How common will it be that we will have an average value of 0 amongst all of the members of a 2 sample? How about a 5 sample? How common would it be for us to have an average of 0? It's pretty common among the individual data points, but how common would it be for there to be an average of 0 for 5 samples, 10 samples, 50 samples, 100 samples? And on the other end of the spectrum, how common would it be to have a sample mean of 100 if we're dealing with a sample size of 5, 10, 20, 50, 100, 200, 500, 1,000, and so on? Hopefully you can see with me that those extreme values get less and less likely as we get larger and larger samples here. And it becomes increasingly more likely that we're going to get an average that's closer to the center here of 50. And that is, in fact, what we discover here. You're going to see this in a second here. This is the raw data. The mean of the data is 50.1985, so pretty close to 50. And there's the standard deviation of just under 30. If we use a sample size of 2, just like what you saw with the dice, it switches now to a pyramidal shape, where the most common averages of a sample size of 2 are around 50, and it's less common to have an average of 0 or 100 in the extremes for a sample size of 2. And we can talk about what the mean is and what the standard deviation here is. The mean is 49.9, the standard deviation is 20. Okay, let's make it a little larger. Let's do a sample size of 5. It starts to look normal. Interestingly, because our original data is not a normal distribution, it's a uniform distribution. And yet, as we start to sample from it and get samples of 5 elements of each one of those, and to calculate the statistics on those, and then do it again, and do it again, and do it again, what we get is something that doesn't look uniform at all. It looks normal. That's one of the elements of the central limit theorem, is that no matter what the original data looks like, when we start to take samples of that original data, it starts to look increasingly more normal with larger sample sizes. Notice we have a mean here, and we have a standard deviation. The mean is again around 50, standard deviation is 13. Now, ask yourself the question, what does it look like? What do you think is going to happen to the standard deviation as the sample size gets larger and larger and larger? Would it be more or less common to have extreme values for the means of when we get a sample size of 10, 20, 50? Ask yourself what that question is and see if the results of this simulation agree with you. A sample size of 10. It's a little bit skinnier. The mean is still the same. It's still around 50, but the standard deviation is now a little bit smaller. If we take a look at a sample size of 20, the mean is still the same, but the standard deviation is smaller still. A sample size of 50. See how this thing's getting skinnier and skinnier and skinnier? That's the idea here. The mean is staying the same, but the standard deviation is getting smaller and smaller and smaller. The sample size of 100. Even skinnier. The mean is 50, the standard deviation is just under 3. A sample size of 200, we're continuing to get more and more skinny. Sample size of 500, look at how skinny that thing is there. So a mean of 50, a standard deviation of 1.3, a sample size of 1,000. I mean, there's only 10,000 samples in the entire population here. So when you're doing a sample size of 1,000, you're sampling a tenth of the population every single time. You're not going to get extreme values for that very often at all. You can get some, but they'll be very, very rare. And that's reflected in this standard deviation. As you can see, it's very, very small. 2,000, smaller still. 5,000, even more so. Now, what's going to happen when we have a sample size of 10,000? A sample size of 10,000. The population itself is only 10,000. So a sample size of 10,000 is the entire population. So we just get one value. It's the population mean. We don't have a standard deviation to that because there's only one value that we can get from that. So let's take a look at this here. Actually, we can calculate the theoretical value for the standard deviation, but in this case, it doesn't really apply since our population size is 10,000 here. But let's take a look at this here. As we took a look at all the sample sizes, let me turn myself off here. If we take a look at all these sample sizes going from 1, 2, 5, 10, 20, 50, 100, and so on, the sample means didn't change very much. And as time went on, you can see that they really got very, very close, increasingly close to the population mean, which is right down here. But probably what's most notable here is you can see that the standard deviation went from being 29 all the way down to a very, very small value. And we can actually describe how much this goes down over with increasing samples here. So as sample size gets bigger, the mean stays the same and the standard deviation goes down. This also means that sample errors go down, and so estimates of the mean are more certain for larger samples. If I'm taking 5,000 samples, I have much smaller margin of error than if I'm just taking 10 samples, as you can see here. So here's the way in which we can actually model this. As it turns out, this drop here is basically a square root of n drop here. So if we start off here with just one sample, this is what we start off with. If we take 4 samples, the square root of 4 is 2, and so this gets cut in half. If we go with 9 samples, the square root of 9 is 3, so this standard deviation becomes a third of what it was. So basically this trend here is a square root of n trend here, where n is the sample size. And so as we get to 10,000 samples here, we get to a point here where this is 100 times smaller than it is here at the top, because the square root of 10,000 is 100. So if we take this standard deviation and divide it by 100, you can see the decimal point moves 2 spaces to the left. Square root of 100 is 10, so you can see here it's actually just moving one decimal point to the left, being 10 times smaller. Okay, so we have this new let me pull myself up here. There we go. We have this new vocabulary term that we're working with now. It's called the standard error. And it's basically the standard deviation, but when you're working with samples instead of individual data values. That's what, so basically when we started off with that initial data set here and you saw all of those distributions getting smaller and smaller and smaller, the standard deviation of each one of those we call the standard error. And you can see here that we use this kind of a notation for this. The standard error is basically the standard deviation of all the possible samples that we might get out of a population where the sample size is n. There it is. Okay, so here's another description of it here. Let me hide myself again. What this is showing you here, whoops, there we go. What this is showing you here are two different distributions. Here's one on the left and here's one on the right. They're essentially the same distribution on top here, but below this, we're taking samples of size 5, and you can see how those samples are distributed here. Some are near the center, but some of them are out in the farther reaches. Each time we do that, we're taking the mean of each one of those 5 samples, and we're adding it to this distribution down here. The same thing is happening over here, except we're working with a sample size of 25 samples. And as you can see, they're spread out pretty much the same way as these over here. But when we average these together, it's a much tighter fit. It's a much more common to have things near the center than it is over here. And so you can see that we are building two normal distributions to describe the statistics. Oh, start it over again. To describe the statistics of the samples taken from this same normal distribution here. But as you can see, the standard deviation, i.e. the standard error of this distribution, is smaller than it is for this distribution. And that's reflected in the fact that we have a larger sample size over here versus over here. So we have distributions of raw test scores showing a given standard deviation. We sample them this way, and the result is that we get two different distributions here from the same set of numbers, but we get two different answers here because our sample sizes are very different. Okay. So as the sample size n increases without limit, the shape of the distribution of the sample means taken with replacement from a population with mean mu and standard deviation sigma will approach a normal distribution. As previously shown, this distribution will have a mean mu and a standard deviation of sigma over the square root of n. Okay, so you can really see here both elements of what we're talking about. This is the original distribution that we're working with here. Couldn't get much farther from a normal distribution than to have two different bimodal peaks here, one on this side, one on this side. That couldn't be much farther from a normal distribution that you could possibly get here. And yet, as we start to get to sample sizes of 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on, as we get larger and larger samples and start to get up to samples of around 30 or so, notice how all of this kind of smooths out into a normal distribution. That's the central limit thing, or at least the first part of it. And then notice as we start to get larger here, it stays normal, but it gets skinnier. The standard error gets smaller and smaller and smaller. Okay, so just as you can compare individual sample sizes with a distribution of sample values, that was our Z statistic that you calculated before, you can also compare an individual sample mean with a distribution of sample means in the exact same way, except your standard deviation that you had before is now replaced with this standard error, which has that square root of n stuck into its calculation. Okay, so here are the two things here. When the original variable is normally distributed, the distribution of the sample means will also be normally distributed for any sample size n. When the distribution of the original variable is not normal, a sample size of 30 or more is needed to use a normal distribution to approximate the distribution of the sample means. The larger the sample, the better the approximation will be. You could see that from this previous figure that we had here, where even when we start off with a distribution that's anything but normal, once we get up to a sample size of around 30, you can see that things get far more normal. Okay, so let's see if we can use this information here. A.C. Nielsen reported that children between the ages of 2 and 5 watch an average of 25 hours of television per week. This is a little bit dated. Assume the variable is normally distributed and the standard deviation is 3 hours. Now look at what's being talked about here before. This is something new. This was something new from what we did with our normal distribution problems in the last chapter. If 20 children are being sampled, in all of our problems beforehand, it was just a single sample, a single individual that we were looking at before. Now we're looking at samples. If 20 children between the ages of 2 and 5 are randomly selected, find the probability that the mean of that sample of 20 will be greater than 26.3 hours. Just like before, we're going to calculate this z statistic, but the only thing that's going to change is that our standard deviation will now be a standard error. Here's how this works. Oh, where's my cursor? There it is. So here's how we calculate this standard error. We have the standard deviation, that's 3 hours. A sample size is 20, so we're going to take 3 and divide it by the square root of 20. And if you do that on your calculators, you should get 0.671. So that distribution has shifted from a standard deviation of 3 to a standard deviation of 0.671 because we're now dealing with a sample size of 20 kids, not just one kid. All right, so the z statistic proceeds exactly as before. We just are working with 0.671 instead of 3, and we get this new z value here of 1.9374. And they're asking here, find the probability that the mean of the number of hours they watch television will be greater than 26.3 hours. So that means we're going to look at the right-hand probability from your spreadsheets here. And so that's going to look like this, where if you put this into your spreadsheets, you should get 0.0262 for your answer. Excuse me. So that's a very different answer than what you would get if you were just asking what's the probability that a single child watches more than 26.3 hours. If you asked that, then this standard deviation down here would be 3. Your z distribution, your z statistic would be much closer to 0, and your probability here wouldn't be so extreme. It's a lot more extreme for an average of 20 of them to be above 26.3 hours than it is for an individual child to be above 26.3 hours. Okay, so here's one that I'm going to give to you to work with, and I'm going to hopefully you can stop the video once I've totally introduced it here. Not yet, but once it's time to do so, go ahead and stop it. The average time spent by construction workers who work on weekends is 7.93 hours. That's over the 2 days on the weekend. Assume that the distribution is approximately normal and has a standard deviation of 0.8 hours. So the number of hours that construction workers work on the weekends is apparently has an average of about 8 hours and a standard deviation of just under 1 hour. So it looks normal that way. Here's what I want you to do. Find the probability that an individual, that's from the last chapter, find the probability that an individual who works at that trade works fewer than 7.5 hours on the weekend. That's the first part. The second part would be the same thing, but for a sample of 40 construction workers, and to ask, find the probability that the mean of that sample of 40 will be less than 7.5 hours. So take some time for that and go ahead and pause the video. Welcome back. Well, if you did this right, you probably noticed very different answers from part A versus part B here. from the difference of just looking at a single construction worker versus a sample of 40 construction workers here. Let's look at this here. What we want to do is, first of all, just calculate our familiar z value here, x minus mu all over sigma, and we get a value of z of negative 0.5375. And we're asking what's the probability that they work fewer than 7.5 hours on the weekend. So this is a probability on the left that you're finding from your spreadsheet that should just be under 30%. Let's do the same thing now for a sample of 40 construction workers. Here it is. The seminally important thing here is that we are finding a standard error, and we get a much smaller number here of 0.1265. That's going to go in the denominator now, and as we're calculating our z value, we're going to get a much more extreme value here of negative 3.3992, and the probability from your spreadsheet there is going to be much smaller, 0.03 of a single percent there. So it's far less likely that you would get a sample of 40 of them with an average that's that low than it would be for you to take a look at a single individual here and to ask whether or not the amount that they work is less than 7.5 hours. Okay, so the average drive to work is 9.6 miles. Assume the standard deviation is 1.8 miles. And if a random sample of 36 employed people who drive to work are selected, find the probability that the mean of the sample miles driven to work is between 9 and 10 miles. So take some time for that. Be aware of your sample size as well as the z values that you'll have to calculate. How many of them will you have to calculate? One or two? There's a little hint there for you. So take some time for this and pause the video if you would please. Welcome back. Well, let's take a look at what this value is here. Again, what we're doing is we are working with finding this new thing called the standard error, which is much like the standard deviation, except that you're taking into account what the sample size is, and finding that things get smaller as the sample size gets larger and larger here. Our value for the standard error for this is 0.3, which means that our two z values here are going to be a lot more extreme than they otherwise would be. We have one z value that's negative 2, the other one is 1.3333. And as a result here, as we're working with this, we get a probability that's in between the two of them here. Remember, the way that you have to do that is to find the left-hand probability values for each one of these and subtract them off. And you should get a value that is 0.4875. So just under 50% probability of finding that the mean of a sample for miles driven to work for 36 people would be somewhere between 9 and 10 miles. That makes sense since the average for the population is 9.6. So we're not exactly in extreme values here for this average. Okay, let's also talk about a couple of correction factors that we made use of when we were doing that work for Professor Howell. These are called the finite population correction factors here. In a study of the life expectancy of 500 people in a certain geographic region, the mean age at death was 72 years, and the standard deviation was 5.3 years. If a sample of 50 people from this region is selected, find the probability that the mean life expectancy will be less than 70 years. Here's an important thing to keep in mind. When we're working with, let me back up, all of our calculations thus far have assumed that the size of the population is infinitely big, or rather just very, very big. If we start to take into account the fact that some populations are in fact not so big, then the statistics change a little bit here. So Here, this is a correction factor that you have to take into account whenever you are sampling a large part of the population. In other words, if you are sampling, let's say, all of the seniors at ECA, if you are sampling, uh, you know, 80 people, 80 seniors at ECA, you're sampling almost the entire population. If you are sampling 80 voters out of the state of Colorado, you are sampling nowhere near the size of the population. So the statistics change just a little bit when we are dealing with a population that's a little bit smaller, like, for example, the size of all the seniors at ECA. So when one is sampling without replacement and the size of the sample is greater than 5% of the actual population, in other words, if your sample size is more than 5% of the whole population, then the standard error of the mean is also multiplied by the finite population correction factor that is highlighted here. So this equation here for the standard error becomes even more complex. What we have is our familiar standard deviation divided by the square root of n, and that's the sample size n. But now we also take into account the population size n, which is symbolized with a capital N, not a small n. So here, the sample size is 50, and the population size is 500. And 50 is 10% of 500. That is more than 5% of the actual populations. So the use of the finite population correction factor is appropriate. And so here is the extra factor that you plug things in here. So n minus n, the population size minus the sample size, that's going to be 500 minus 50. And down here, the population size minus 1 is going to be 500 minus 1. You're going to take the square root of this fraction here and multiply it by what you already have, and your standard error is going to get even smaller here, just because of the fact that if your population is so small that you're actually sampling a very, very large portion of it. Hence, there shouldn't be a whole lot of wiggle room in the results from all your statistics. So this brings down your standard error even more, considering the fact that you're working with a finite population. And let me do this here. That can affect what your z-score is as well as the size of your probability. That find the probability that the mean life expectancy will be less than 70 years. This wouldn't be nearly as small if we didn't make use of this finite population correction factor. Okay, so a study of 800 homeowners in a certain area showed that the average value of the homes was $82,000 and the standard deviation was 5,000. So we're going to assume that that's the population here. If 50 homes are for sale, find the probability that the mean of the values of these homes is greater than 83.5. Boy, these were the days, weren't they? I'm told that Zeke is the person who's filling in for me here today. Wasn't it nice when homes were like a manageable size for good grief? This is about when I was a kid. This is pretty much what the value of a home was in dollars back then. Should the finite population correction be used here? Why or why not? Well, we're sampling 50, and there's 800 homeowners here. 5% of 800 would be 40, and we're sampling more than 40. So we should use the finite population correction factor here. And so this is just a way of describing what I just did here. The sample size divided by the population size is 6.25%. That's more than 5%. So make sure you know how to do this. There are some elements in the homework where they ask you the question, should the finite population correction factor be used here? And you have to be able to answer that. So here is our value for the standard error. And it's got the standard deviation, square root of the sample size, and then our finite population correction factor. And when we do that, we get this value here for the standard error. Here's our z-value, 2.1895. It's a pretty extreme z-value there, and so I'm guessing that our probability statistic here is going to be pretty small, about 1.5%. So there's a 1.5% probability that the mean of these 50 homes will be greater than 83.5. That kind of makes sense with the average being 82,000 and the standard deviation being only 5,000. And the fact that we're sampling, not only are we sampling 50 of those homes, so based upon that alone, we should have a pretty small standard error. But the fact that we are sampling such a large percentage of the whole population, that should make the standard error all the smaller. Okay, so let's bring this back here to all of the things that we've been talking about. Think about what some things should go um, into your cheat sheet here. How distributions of sample means change when sample sizes get larger, as well as how does the shape of the distribution change as sample sizes get larger and larger. How do standard errors change as sample sizes get larger? How do you calculate z-values and probabilities from distributions of sample means? And when and how do you implement the finite population correction factor here? So think about what those equations are that we've come up with. We now have a version of, well, we have this new thing called the standard error, and we know how to calculate it now. We know when to calculate it. We calculate it when we're dealing with samples instead of individual data values here. We know from the central limit theorem that as those sample sizes get larger, that standard error is going to get smaller and smaller. The distribution is also going to get more and more normal. And so we have this formula for the standard error, and we have another version of that formula for the standard error when the finite population correction factor is appropriate. And just to come back to the spreadsheet here, if I were to show you this here, notice the sample size place here. This just basically implements the standard error of the mean correction when you're dealing with a sample size that's larger than 1. So if I put in a sample size of 4, the square root of 4 is 2. So the standard error of the mean below this should be smaller than that. It should be, oh, come on, figure it out, 2.5. Yes, very, very good. So it's 2.5 instead of 5. So if you were wondering, all this time it was actually looking at the standard error of the mean down here, not at the standard deviation that you were putting in. And so that's why I told you to make these things equal to 1 all the time here. So you can see here that it adjusts what these normal distributions look like based upon the size of the sample size. So you can make them skinnier and skinnier by making the sample size larger and larger. You can see how the distribution of the sample means is going to be a lot skinnier than it is for the distribution of actual data values. Okay, so let's also pull up the assignment on this here. Let me see if I can pull this up quickly. I'm pulling it up for period 2, but the one for period 6 is exactly the same. So you'll find this on D2L. There'll be it'll be under homework 7.1a. And you're going to have a set of videos just like before. And remember, all this stuff under guided practice is extra credit. If you want to watch the videos and work with this, there's a number of really, really good videos on how to do this. There's some guided practice for this. And then there's the actual independent practice assignment here in which you're going through a set of problems along these lines here. So I think that there are only, yeah, there's 10 problems in the independent practice and just a couple of well-involved problems for the guided practice here. So hopefully that is all of what you need here. So spend the rest of the period working through all of those, and I'll see you tomorrow.